So now we're going to look at some characteristics of functions. So, bear with my writing. You know how this goes, right? So let's see. Oops, you know what? I have this upside down. That would not have been good. All right, so let's increasing, decreasing, and constant. Let's take a look at what that means. So as you look at a graph, and that we're going to do that from left to right, just like how we do when we're reading. Right. That's going to be, we're going to be increasing our x values then. Increasing the x values. The graph is described then, the graph is described as increasing, decreasing, or constant. And that's going to be done by its y values. Now let's go and see. So if we describe the intervals, of increasing, decreasing, and constants, of increasing, decreasing, and constant. And we're going to do that with interval notation, where we're describing them just by their x values. So with interval notation, with interval notation, which is of the x values. It seems weird to not use the y values, because that's the y values determine whether it's increasing or decreasing or if it's constant. But we're going to say it's constant y values on these x values, or it's increasing values, y values on these x values. So we're going to be using just the x values to those. So let's take a look at the graph that's down there. And we're going to state the intervals on which the given graph is increasing, decreasing, or constant. So the first thing I want to look at, let's look at increasing. Increasing. So it's increasing starting, at this arrow and going all the way up to here. So I'm going to say it's going to be, that arrow means it keeps going further and further back, so we're going to call that negative infinity. And then it stops increasing at -2. No, -1. I'm sorry, I can't even read my own graph. -1. And when we're describing those intervals, we're going to use parentheses every single time. And then we're going to have decreasing. From this point 1 all the way down to here, to 1 to 2. And then in between that, from -1 to 1, that's just constant. So let's put that down here, constant, from -1 to 1. But from 2 all the way to infinity, it's also increasing. So we're going to put a u here, and then we're going to put 2 to infinity. There we go. Yike. So record. There we go. Okay, so I'm going to look at the relative maxima and minima, or they're also called extrema. So when we're talking about both of them at the same time, maximum is going to be the highest, minimum is going to be the lowest. So and relative means that it's going to be local. So let's just write that word local here. Because it's not necessarily the very highest or the very lowest one. It's like the highest one in its neighborhood or the lowest one in its neighborhood. So let's take a look at these. I'm looking at this particular graph that's been given to us, and that function is called f of x. So we're going to say the function f has a relative maximum has a relative maximum at, and it's right here, -2. And the relative maximum is relative maximum is, and how high does that go? On the y-axis, it only goes to 0. So we're going to say the function at -2 is 0. The relative minimum, it also has one of those. So f has a relative minimum. And that's going to be at, and that's the x value here is 1. Oops, at 1. And the relative minimum is whatever the y is at f of 1, and that's going to be -2. I want you to just really take a note here that when I say where something is, you're going to tell me at and then give me an x value. If I ask you what the maximum or minimum is, you're going to say it is, and you're going to give me a y value. That's really important to know what we're asking for on each of those when I ask where or when I ask what. So here we are. Now we're going to look at even more characteristics. We're going to look at even and odd functions, which has to do with their symmetry. First things first, we're going to look at an even function. You know, you've done an even function before. An even function was the cosine function. So that's the one example that we're going to use. So an even function, algebraically, it means that f of -x is the same thing as f of x. So this replacement makes no change to the function. And that means that if they are an even function, they are symmetric with respect to the y-axis. Respect to the y-axis. So let me give you a couple of examples, and keep in mind that my drawings are going to be a little wonky because I'm drawing on a computer. And so, like I said, just at the beginning of this, the cosine function is, oops, see, I told you it was going to be a little wonky. Pretend that those are beautiful, but if this is the y-axis right here, that is going to be where you can fold it, and it will match, or it's a mirror image. Let's do another one. Another one would be like g of x is equal to x squared minus 1, which looks something like this. And it's not a perfect drawing either, because, you know, yeah. But that, once again, if you were to fold it on the y-axis, you'd have a mirror image there. And then we get to our odd functions. And you've seen those too. But let's take a look at what we might, there we go. Algebraically, the function of the negative x is going to be the opposite of f of x. So this means that when we replace x in there, it replaces all the signs in the terms of the function. So everything that's positive in that function becomes a negative, and everything that's negative becomes a positive. Now, odd functions have a symmetry as well. So odd functions are symmetric about the origin. And in trigonometry, we have another one that's like that, and that would be f of x is equal to sine x. Looks something like that. And that one, if you were to turn it upside down, so if you were to lock the aspect, if you're watching this on your phone, and then turn the phone around, then it would look the same. So turn it around 180 degrees, and it looks exactly the same. Another one would be something like this one. G of x is equal to x cubed, which looks something like this. And once again, if you were to rotate it around the origin 180 degrees, it would look the same as it does, the way it's drawn. Okay, so we're going to do some examples. We're going to determine whether the function is odd, even, or neither. Now, there's a little trick, and I'm telling this is from me to you. When you're looking at a polynomial, not a trig function, a polynomial function that has x raised to some exponents, there is a really, really easy way to know whether it's odd, even, or neither. And I'm going to let you in on the secret. Here we go. The secret is, shh, don't tell anyone. If the exponents are all positive or all even, it's an even function. And if the exponents are all odd, it's going to be an odd function. Not hard to remember, is it? What if you have both? If you have both, it's not going to be even or odd. It's going to be neither. And one other little thing. 0 is an even number. All right, I've let you in on the secret. Let's find out if we can do these. This first one, x squared plus 6. Well, the exponents are 2. Well, this is the same thing as 6x raised to the 0, because x to the 0 is 1. So the other exponent is 0. This is even, this is even. So the function is even. Let's take a look at b. We've got 7x cubed minus x. Well, the exponent on this first one is 3. The exponent on the second one, if there isn't one, you assume it to be 1. So the exponents are 3 and 1. Those are both odd. So this function is odd. Then we come to this one, x to the 5th times x, or plus 1. Now, this one has a 5 as an exponent. Remember, 1 is going to be written as 1x raised to the 0. And we had said that 0 is even. So this is odd. This is even. Since I don't have one or the other, this one is neither. Hopefully you won't forget this rule. This rule is pretty easy.